welcome everyone. It's a great pleasure to have Professor Saurabh Jha here today. Thanks a lot for accepting our invitation. Saurabh is a distinguished professor in the Department of Physics and Astronomy at Rutgers University. He earned his PhD in astronomy at Harvard University and later held research fellow positions at the University of California, Berkeley, as well as LAC, where he was a Panofsky Fellow and a full member of the Kavli Institute for Particle Astrophysics and Cosmology. He then joined Rutgers University, where he is now based. Among his major honors, Saurabh is a recipient of a Guggenheim Fellowship and has been named a Fellow of the American Physical Society, Fellow of the American Association for Advancement of Science. He was also a member of the teams awarded the Gruber Cosmology Prize and Breakthrough Prize in Fundamental Physics for the discovery of cosmic acceleration. His research is mainly on Type Ia Supernovae, both in measuring distances for cosmology and in understanding the astrophysics or the progenitors and explosions. Today, he will present cosmology with Type Ia Supernovae, near and far. Saurabh, please, you can start when you're ready.
Great. Thank you very much, Eleonora, for the invitation and for everyone to join. Great. Okay. So again, thank you for the invitation. I'll talk a bit about Type Ia supernovae and their use as distance indicators for cosmology, and I'll highlight some kind of new directions that we've been looking at and focus on sort of the systematics limiting their application for cosmology. So I wanted to start with this beautiful image. This is an image taken with JWST with MIRI in the mid-infrared of a nearby Type Ia supernova host galaxy, and and you can actually see the supernova there after his faded a bit in the corner. And this is one of the objects that we've been studying with JWST to learn about the physics, the astrophysics of the progenitors of Type Ia supernovae. And one of the things that comes up all the time when we talk about supernova cosmology is that, we still have this only rudimentary understanding of how these white dwarfs explode. And isn't that a problem for the application of these objects to cosmology? And I'm going to try and argue yes and no today, that for many measurements, we don't need to know the detailed astrophysics of what's going on. But as we go to higher redshift, as we approach, the higher and higher precision in our desire to get higher and higher precision and accuracy, then maybe those astrophysical effects are, now we're seeing that they're gonna play an important role. So I want to have kind of both sides of that story today. Okay, just, I don't know if the background of everybody, I know this is quite a broad series, and so I know I see some supernova experts in the crowd, but just to have everyone on the same page, the way we survey the universe with supernovae, and literally surveying, measuring distances to extragalactic objects with supernovae, goes something like this. So you observe some galaxy, you observe it later, and you see that one star in that galaxy has exploded. You take a spectrum and you see this pattern. Now, we understand this pattern to be the explosion, the ashes from nuclear fusion of carbon and oxygen, making this pattern of elements, intermediate mass elements like calcium and sulfur and silicon that we see, and then also iron group elements. And during the explosion releases energy, the kinetic energy of the ejecta, something like 10,000 kilometers per second. The expansion velocity of the ejecta, something like 10,000 kilometers per second. So we see these broadened lines of these species, and we can identify this thing as a Type Ia supernova. And again, so part of this is that if you just see this pattern, you go out and you observe a supernova, you see this, take a spectrum, you see this pattern, you can just call it a Type Ia supernova. And you don't have to know what kind of star exploded or what these elements are or, what the process was to use them as standard candles. And I'll explain why that is in just a second. Okay. So we observe their spectra. To classify them, we observe their light curves. They go up and down. It takes about 3 weeks for the supernova from explosion to the peak, and then they fade away. And at late times, the decay is governed by radioactive decay of the elements. But again, in our approach of using supernovae as empirical, standardizable candles in the universe, again, you don't necessarily need to know all the details of what is going on physically to still make good cosmological use of them. Okay. So there are, of course, some challenges with using supernovae compared to other distance indicators. Supernovae are rare, so a typical galaxy like the Milky Way will host a Type Ia supernova every, maybe a few hundred years. They are unpredictable, of course, so we can't point our telescopes and knowing that there will be a supernova in a particular place. And they're fleeting; they don't last forever, so you have to catch them while they are bright. So those are the challenges, but those challenges are outweighed by the precision that they give, and so that's the reason that they're still playing a starring role in cosmology today. And that precision is indicated here. So what you can do with these supernovae, and an important sample of these supernovae are the ones in what we call the smooth Hubble flow. So relatively nearby, but not so nearby where peculiar motions, peculiar velocities affect the redshift that's observed. So if you go out into the smooth Hubble flow, so maybe past redshift zero point 0.02, zero point 0.03, people have different standards of where they want to start. But if you go into the smooth Hubble flow, where redshift is just proportional to distance, you can find a sample of these objects, and you can just, again, without knowing what they are, you can just plot them up in terms of their luminosity and their redshift. So that's what's shown in this Hubble diagram here, velocity in kilometers per second, peak apparent magnitude, so just their observed flux. Right? And again, if they were a perfect standard candle, what you would see is that whenever the redshift was twice as much, so if you had a supernova at redshift zero point 0.03 and another one at redshift zero point 0.06, you would always find that the one at redshift zero point 0.03 was 4 times as bright as the one at redshift zero point 0.06. Again, not knowing anything about what this object is, just by observing these properties, you could test that hypothesis that they are a good standard candle. And that's what this plot is. Just plotting the peak apparent magnitude of the supernova versus the redshift. And again, if because redshift is a linear with distance in the nearby universe, you would expect all the objects to fall on that line that you see there. Okay? And they mostly do, but with a scatter of about 22%. And so that's a little bit high. So what we would want to do is see, okay, can we improve that? And that's what you see on the left-hand side. So these are versions of what's called the Phillips relationship, where you plot that peak absolute magnitude of the supernova against some other property. And in this case, the property is how fast the supernova declines after the peak, this delta M15 parameter. And what you can see then is there are some patterns, especially, for example, here in the B band, that there's a correlation between the supernova peak absolute magnitude and this decline rate. Okay, and again, completely empirical correction. You can use this correction to make your standard candle even better. And so that's what we do. There are many ways to do this. I worked on one with Adam Rees a long time ago called MLCS. But the one common one that's used nowadays is the SALT 2 model. That's what's shown here. So you take your light curve observations of your supernova, you fit it with this light curve model, you get some parameters, in this case x1, which describes the shape of the light curve, and c, which describes the color of the supernova, and you make an empirical correction based on those parameters, basically making a plot like this, finding, there's a pattern that correlates peak absolute magnitude with these parameters, correcting for that. And then you can get this sort of standardized version of the Hubble diagram, so using them as standardized candles. Okay? And you can see the scatter improves quite significantly from, say, 22% to 9% in this particular compilation. Okay? So again, this is completely an empirical correction based on the light curve shape and color that makes the supernovae better distance indicators. And again, we can test this completely in that smooth Hubble flow where we know that the redshift is a good proxy for distance. Okay, so we don't need to know anything about the absolute magnitude or calibrators for this part. We can do the standardization in that smooth Hubble flow to figure out these relationships. Okay, one thing to point out is that this is what the standardization looks like. You take that peak absolute magnitude in B band, you multiply it by a coefficient alpha times this x1 parameter, the shape of the light curve parameter, and then you subtract. Of course, this minus sign is always why the signs are different here is just a historical legacy, which I wish it was not like that. But anyway, then you subtract this beta parameter times c. So alpha and beta are just constants based on your supernova sample, and x1 and c vary from supernova to supernova. And this is your corrected absolute magnitude that you put on the Hubble diagram. Okay. So one thing to note, and so the history of this, this correction here with the decline rate, that Phillips relationship, that's taken to, have been, kind of the key factor turning supernovae from standard candles to standardizable candles. And that's certainly true in the history. But as we collect bigger and bigger samples, it turns out we don't have to use the full range of X1. And in fact, in modern cosmological samples, we generally limit the range of objects we use, the supernovae we use, to an X1 region, something like this. So maybe X1 of -2 to 2, and then a color region, something like this. Okay. And actually, if when you do that, when you limit the decline rate, you limit the objects that you put into the supernova sample, and that's going to be a theme of the talk, you can get a more homogeneous population. And in fact, actually, what you find is that the color correction, this beta times C, is generally a bigger correction on average than the alpha X1 correction. So in fact, the color gives the largest correction for supernova cosmology analysis. It means that when you take your observations, you want to make sure you measure your supernova colors, you do your photometry as precisely as possible, because this color correction dominates actually over the X1 correction for modern samples. It wasn't always that way, but nowadays the color correction is the dominant one. Okay, so you do that, and then you can do all this cosmology. And so, well, I'll talk about H naught and a little bit about dark energy in the talk. But just to push this point of, again, everything on that previous slide did not require any knowledge that this was a white dwarf exploding, or whether it was at the Chandrasekhar mass or not when it exploded. That's a big open question actually right now in the progenitor physics, right? All of that just depended on being able to make these observations in the Hubble flow. Okay. And so when people ask, okay, well, there's this discrepancy, in the Hubble tension, and part of it relies on supernovae, and we don't understand supernovae, isn't that a huge problem? Isn't that the reason why there is a tension? And I think the answer to that is definitely no. That the fact that we don't understand Type Ia supernovae as well as we might is not the direct reason for the Hubble tension, at least in my opinion. And this slide kind of illustrates why. It's because when we make a measurement of the Hubble constant, we have these Hubble flow supernovae around redshift 0.05, so a few hundred megaparsecs away. And we have to now calibrate them with some known distance. And so we have this distance ladder with two lower rungs, one with calibrators, for example, Cepheids, and then geometric anchors on the first rung. Those calibrator supernovae are at distances of 20-ish megaparsecs. Okay, so there's not a huge distance in time or redshift between the calibrators and the Hubble flow that would allow a huge systematic to come in where the supernovae are very different in the Hubble flow compared to the calibrators. And in fact, we can work to make sure that the samples we use in the calibrators and the Hubble flow are as similar as possible. Okay. And in fact, if you think about it, the Hubble flow itself, if you go from, let's say, redshift 0.03 to 0.08 or redshift 0.02 to 0.1, that range is actually a bigger range in the Hubble flow where you are doing all the standardization. That is a bigger range than the mean of the Hubble flow to the calibrators. So any kinds of systematic effects that you might think from the supernovae should show up in the Hubble flow sample itself. You should be able to, you have some hypothesis that there's two kinds or whatever, and we'll talk about that. All of that should be testable within the Hubble flow sample itself before you do the H naught. You really have to argue for something special that's different about the calibrators from the Hubble flow if you want to break this and make that the source of the Hubble tension. Okay? So I think that's one argument. Another, perhaps even more clear, convincing argument that the supernova themselves are not necessarily the thing that is causing the Hubble tension is that now we have many, many other observations that don't include supernovae at all in the local universe. So surface brightness fluctuations, Tully-Fisher, masers, etc., that also give a higher value of the Hubble constant. Okay, so I think those two lines of evidence say that we are using the supernovae well, not perfectly, and I'll describe that in just a bit. But in terms of the source of the Hubble tension, our lack of detailed understanding of supernova astrophysics is not the primary cause. Okay. So this is a paper from Adam. I see Adam's online. So just showing that as we get better data, going from HST data to JWST data, of course, things improve and you can cross-calibrate, and so things work out. I will refer you to that paper. The reason I wanted to highlight this, some of the figures here, is just to show these plots in the middle. And even with the calibrated supernovae, the scatter is something like 0.1 to 0.15 magnitudes. Okay, so each supernova by itself will give you a different value of H naught, or however you want to think about it, with some scatter, something like 10% in distance or 7% in distance. Okay? And so when you plot a bunch of them, you will see a histogram and you will get a wide range, going, more than 10% across. If you have a big enough sample, you'll start to, fill out that whole range. Okay. And so this is important because as we try and do subsamples, for example, if we try and narrow things down, we really need to contend with the fact that the supernovae themselves have some, intrinsic amount of scatter within them, and that is something you have to, deal with. And so, in fact, the reason why the Hubble constant with the supernovae is, it's limited so much in terms of the precision is mostly because of the number of objects in the calibrator sample. You take the overall the scatter per object, divide by square root of n, you still have, this you're approaching now 1% in precision there, but it's because you need that sample to bring that scatter down. Okay. So one of the things I'm going to talk about is like an alternate ways. Can we find a way to reduce this scatter in the supernovae? Can we be clever finding either subsamples or using different techniques to reduce the sample to, be able to, not be susceptible, for example, to if your subsample just happens to be these objects in red versus these objects in blue, you'll see that you'll measure an H naught offset. Okay, just from subsample selection or just which objects you use because you're sampling from a distribution that does have some width to it. Okay? So I just want to keep that idea in mind. Okay, so let's get to the systematics. There are many systematics in Type Ia supernova cosmology. There are a lot that have to do with calibration and measurement, and I'm not going to talk about those. I want to focus more on astrophysical systematics. And so this very busy plot, which I don't want to go through all the details, but basically shows, for example, many different ways that the Type Ia supernova luminosities depend on their environment, and in this case, on their host galaxies. So there was some early work that showed, for example, if you looked at the stellar mass of the host and you looked at the standardized luminosity of the supernovae, there seemed to be a trend. This is something Pat Kelly saw a long time ago now, that the more massive host galaxies, stellar mass, seem to produce slightly more luminous supernovae. And that was confirmed either in stellar mass or if you look at star formation rate, the more massive galaxies also tend to have lower star formation rates. So you can again see this kind of trend. Okay. And there are a bunch of different ways that people have seen this. I want to point out this other paper by Carl Detman is it's not just the standardized luminosity, but there are clearly intrinsic differences between supernovae in these different environments. For example, we can see differences in the velocity of the ejecta. And that's obviously something that's not related to distance or anything like that. That's some intrinsic property of the supernova. And again, it correlates with the environment. So there are many indications then that the supernova environment plays some role. And as environments for supernovae change over cosmic time, you might think, okay, this might be an effect that's important for supernova cosmology. So we're going to dig into that a little bit more. Okay. Again, I mentioned that those luminosity corrections were after standardization, but you don't have to do the step after standardization. Again, you can look at the actual properties of the supernovae and see that they vary with environment. So this is a paper from Connor Larison from last year, where he looked at Type Ia supernovae in the relatively nearby universe in the Hubble flow, which were in clusters of galaxies. And it's been known for a long time, actually, back from the Kolantalola survey and work by Mario Hamwi, that if you look at a sample of more massive galaxies, like massive elliptical, non-star forming quiescent galaxies, they have a different distribution of decline rates for the supernovae. You get more faster declining supernovae in those environments. Okay, and that's what's shown on the lower panels here. If you look at field galaxies, if you look at field star forming galaxies, this X1 parameter, this light curve shape parameter, is quite different for objects in star forming galaxies than in quiescent galaxies. Okay, so this is again from Connor's paper. Connor went a step further, though, and said, well, this is the host environment, whether it's a star forming or a non-star forming galaxy. But what about a larger scale environment? What about, things in clusters? And what he found is objects in the inner parts of clusters are even more skewed in this decline rate or light curve shape distribution. Okay, so about 75% of the ones in the center part of the cluster are these fast declining objects. Okay, and in fact, it might be close to all of them, nearly all of them, because there's projection effects in this sample. So, we don't, maybe these ones are just the ones that happen to be projected in front or behind near the cluster center. So it's hard to figure out exactly how many of those there would be. But if you make some reasonable correction, this fraction of very fast declining events at the centers of nearby clusters of galaxies might be as high as 90-95%, something like that. Okay. And so the question is, okay, what is causing this? Maybe it doesn't matter. Maybe if you make the correction, the standardization with X1, this all goes away, or maybe not. And so a lot of people have been looking at this, doing different kinds of tests, maybe separating the populations into two, like is done here, and treating them separately. And so that may be a way forward to deal with this kind of thing. And you can look at the papers that are cited here that investigate this further. Okay. So the question is, what was causing this? It turns out this is not as prominent at high redshift. This seems to be more prominent nearby. And so one possibility is that maybe it is a progenitor age effect. The supernovae at these centers of these clusters of galaxies, these are the oldest stars kind of in the universe, the oldest populations. They could be the oldest supernovae. And it could just be that older populations of stars, supernova progenitors, produce faster declining explosions. Again, we don't have a good causal reason why that would happen, but that's what the observations seem to suggest. Right? And then this has implications for higher redshift because those oldest objects obviously are not there at higher redshifts. So I'll come back to that. So when we make these investigations, we're learning these things that even with the empirical level, we see these trends, and we have to decide, okay, how important are they for different applications, for H naught, for dark energy, et cetera. Okay, one thing actually is that when you study a sample of these faster declining objects, and by the way, in the X1 SALT2 notation, the faster declining things have negative values of X1, so they're over here, so -1, -2, -3. You can see that they dominate this inner cluster quiescent population, are dominated by these faster declining objects. And one thing that Connor noticed, actually Peter Garnovich noticed this before, because Peter Garnovich was looking at a sample of Type Ia supernovae to calibrate with surface brightness fluctuations, and that also naturally gives a more elliptical galaxies, more early type galaxies in that sample. And so you can see the sample here, and again, they find that same, that they're coming out at these faster declining objects. But one thing that they saw is this correction that I mentioned from the SALT2 model, which should be a linear correction, alpha times x1, doesn't really appear to be one linear correction once you get to these fast declining things. They argued that there was a break here and that it was a steeper correction. The alpha is steeper, a higher value of alpha for these fast declining objects. Okay. And in fact, in Connor's work, we see the same thing, that the alpha, the slope you get here for the fast declining objects is steeper. And this was confirmed very nicely by a paper by Jean-Alain et al. Using the ZTF sample, which I'll get back to also. Again, a steeper slope for these faster declining objects. So we plotted our plot, Connor's plot, the same way as Peter Garnovich did, and so Jean-Alain's I had to flip it around, so that's why it looks like this. But anyway, again, you can see the steeper slope for the fastest declining objects. And so now you might think, okay, well, if the standard correction is just alpha times x1, this is going to be a problem for these objects, right? We need to have either two alphas, a broken thing, or maybe a x1 squared kind of correction. So that's something that might be added to future cosmological analyses, and it may change things. Now, it turns out that if you look at the X1 distributions, because these objects come from these potentially older populations, when you look at the big cosmological samples, like Pantheon or whatever, the bulk of the objects are in this part of the distribution. So this difference in alpha is not going to be a huge change to cosmological results, but it is something we have to worry about, and it's something we have to worry about, especially when we have samples that highlight that include many objects from this region. Okay, so this is just to say that we are continuing to push on the models and trying to improve them to understand what are the supernovae telling us, how can we improve the scatter from the supernovae, how can we make them better standardized candles. Okay, so I'm going to show you one application of these ideas. So one of the tensions that have come up is that maybe there was this difference between what you got for H naught using a Cepheid calibration versus a TRGB calibration. And in particular, like the CCHP, H naught's getting closer to 70 versus the SHU Cepheid ones getting CCHP TRGB calibration getting an H naught closer to 70, like this one here, compared to the SHU's Cepheid calibration, coming in at 72, 73. And so maybe that was something to do with the TRGB versus Cepheids. But actually, if you look back at that paper, the Adam Rees paper using the JWST, it turns out that the difference between Cepheids and TRGBs, there's some, but that wasn't completely explaining the difference between these two results. Some of the difference between these two results was coming from the supernovae themselves. And part of it was which part of the supernova distribution was being sampled by the different samples. And if you use a bigger TRGB sample, then things come back in line. That's a paper by Xiang Li from this year. You can look at that. Okay. And so, but anyway, the important thing is that supernova sample choices can make a difference. Okay. And so for a while, it was portrayed as a Cepheids versus TRGB thing. Now it became like, okay, which supernova samples? So the question is, how can we move forward with this kind of approach? And one issue that you run into here is that one thing that's very good for cross calibration is that there are many supernova calibrators that have both Cepheids and TRGB. You can do TRGB to the halos of star-forming galaxies. So the same galaxy where you measure Cepheids in the disk and TRGB in the halo, right? You then can just compare those distances. That's something that was done in those papers. And so that's great. You don't have to use the supernovae at all. You can just compare Cepheid versus TRGB and see if there's any systematic offsets there. Okay. But the fact that there are many of these galaxies that have both Cepheids and TRGBs means that if you make an H naught analysis using the supernovae, well, it's the same supernova in that galaxy. And as you see here in this plot, the supernovae have some variation in their own brightnesses. And so if you use the same supernovae in both the Cepheid measurement and the TRGB measurement, now you're going to correlate the inferred Hubble constant because of that. Okay. And so, that's good for cross comparison. But if you want a truly parallel, let's say you want a Cepheid supernova distance ladder and a TRGB supernova distance ladder, it might be nice to have a sample where those were actually separated. And so that's something that in a paper with Max Newman that came out just a few months ago, that's something we looked at. And so we tried to make this more independent, not completely independent because we still have the anchors, etc., but a more independent parallel distance ladder using TRGB distances, focusing on massive quiescent supernova hosts. Okay, and the idea is that with these kinds of host galaxies, there are no Cepheids, there are no young stars in these galaxies, and so TRGB is kind of the best secondary distance indicator to use for these, and SPF and others as well. But you can do TRGB to these kinds of galaxies. And so we had a sample of 5 of quiescent galaxies. Max measured TRGB distances using HST and also JWST to 4 of them. We had some data from the literature. You can see the details in the paper, the references there. But the idea is to try and do this more parallel distance ladder. Okay. So the approach here was, okay, TRGB distances to nearby SN1A host galaxies, but only the quiescent massive galaxies, which, you didn't have Cepheids in them. Okay, and here's an example. So you can really measure the TRGB very well, and you can, Max is the expert on that, so you can talk to him and look at the paper for details about that part. Yeah. And then you want to, of course, combine this with a Hubble flow sample. And here's where there's a bit of danger, because we are now selecting a calibrator sample that has properties that are different than average, right? They are massive quiescent hosts. And I was just telling you that when you look at hosts like that, these issues crop up, that you get many more fast decliners, for example, low values of X1, and there might be this steeper X1 correction. Okay, so we need to be able to have a Hubble flow sample that matches the calibrator sample. And this was a problem because when the Hubble flow sample is just a few hundred objects and you're picking calibrators with very specific properties, finding objects in these massive quiescent hosts, you'd really like to have a Hubble flow sample of hundreds of objects just like that. Okay, and we didn't really have that until very recently. And very recently, the ZTF DR2 sample came out with a few thousand supernovae in the Hubble flow, about 1,000 up to their completeless limit, which is around redshift 0.06. And that's important for us because we're going to study fast declining ones that are a little bit fainter than average. So we want to make sure we're complete. And so we call the sample at redshift 0.06 to this complete sample. And there's still about 1,000 objects there. And then what we do is we can make a selection that is like the calibrators, okay, in whatever properties we want. Again, we can do this empirically. The first thing is we say that the host galaxy in the Hubble flow should just also be a massive quiescent galaxy. So we make cuts like that, and that brings the number down from 1,000 supernovae in this sample to just a few hundred. Okay? And in fact, we make some further cuts in our analysis. We want the Hubble flow sample to match the calibrator sample as much as possible. Okay, so here are three parameters: the SALT X1, the color from the supernova, and the stellar mass of the host. And in black, you see the calibrators, okay, the ones that we measured, the TRGB. And so the idea was, okay, we'll pick the Hubble flow, those are the ones in blue, to match that. So we made cuts in X1, cuts in C, and cuts in stellar mass to kind of get a Hubble flow sample that is matched in properties with the calibrators. Okay, and you can make different choices of cuts in the paper. You can look at different things. For example, you see that the C distribution for the calibrators is actually quite narrow. So, you can make a cut, and we did in the paper, a very tight cut. Of course, the sharper cut you make, the fewer objects you have in the sample. And so there's a trade-off between statistics and potential systematics there. But the idea here was, okay, make a sample that is as similar to your calibrators as you can. And we're specifically picking this sample of calibrators from these massive quiescent hosts. So we want our Hubble flow sample to match that. Okay. And another very important point is then we have to redo the standardization. In this case with alpha and beta, and we also looked at a host mass correction. Okay. Redo the standardization for this sample. Okay. And that's very important. So, for example, you see in the X1 standardization, right? This is where we think the X1 standardization is steeper than the overall. And you can actually see that if you look at the fainter blue points, you can see that if you were to continue this to higher values of X1, you would not get this steep slope. You would get a somewhat shallower slope, maybe something like this. But because we're going to focus on this subsample, we want the correct alpha value for that sample. And of course, we marginalize over that alpha in the cosmological fit. Actually, you also see it in the C, the beta parameter from, beta is a color correction. It has something to do with intrinsic properties of the supernovae. Well, we're choosing a sample of supernovae that are intrinsically different, right? They have faster decline rates. Maybe it has something to do with dust. Well, we're choosing a sample of supernovae in massive elliptical galaxies. Maybe the dust properties are different. There are many papers on this idea, right? So you might expect that the beta parameter also would be different. It turns out it is a little bit different than the overall, but not so much. Actually, you can see if we extend it out to redder colors, maybe the slope would kind of go a little steeper here, but in the region that we chose, you get a slope like this. And again, we marginalize over this, so this is included. The uncertainties are included in the fit. And then you can read the paper. It turns out we still saw some evidence of a mass correction here, a slope. So we included that again in the fit, and you can turn that on or off and see the results. Okay. Okay, so you take these cuts, you apply them to the Hubble flow sample, and it turns out you still have 124 objects, a great sample. Since we only have 5 calibrators, having 100 objects in the Hubble flow, terrific. A great sample to do cosmology with. Okay, and one of the cool things to see is now with just here are all the objects. There are a couple outliers that we exclude. Okay, but the bulk of them are really tightly distributed. And if you look at the scatter here, 0.106, that's quite a bit, it's a little bit better than you do with the typical Hubble flow sample with all your objects. Okay, that usually those numbers are something like maybe 0.12 in the best cases, 0.15, even 0.18 magnitudes for the Hubble flow scatter. So by taking this homogeneous sample with the host galaxy and X1 and C, we have gotten a very small scatter in the standardization. Right. You can see here, like, for example, like, the other objects scatter about quite a bit more than the sample that we chose. Okay. And the sample selection was not based on that. The sample selection was based on just cuts in X1, C, host properties. Okay. So that was something that came out of the analysis, that you get this very small scatter. Okay, it's also a testament to the ZTF survey, and so I want to shout out this paper and all the ZTF team members for a great data set where you can see, this wouldn't happen if there were big issues in the data set. To get such a small sample, small scatter from this sample, that's a really great data set to work with, and we're looking forward to, more and big surveys like that and releases in the future. Okay, and so then you can just apply this to get the H naught. So we have the TRGB distances based on the TRGB calibration. Read about that in the paper. Here are the calibrators, 1, 2, 3, 4, 5. Actually, this one galaxy, NGC 1404, had 2 supernovae in them. We think this one is an outlier. I can talk more about it if you'd like. So we did not include it in our final analysis. We tried to be rigorous about our outlier rejection and doing everything blinded in terms of picking our cuts. So this falls out naturally from that. We did the blinded analysis before looking at the H naught answer. Anyway, so that rejected this one as an outlier. So that leaves us with these 5 calibrators. Combine that with this Hubble flow, we get H naught of 75.3. Okay, so relatively high value. We have the uncertainty is it's not 1%, it's a few percent. Part of this is driven by actually our calibrator photometry is based on measurements that we collected various other places like Las Cumbres Observatory, etc., whereas the Hubble flow photometry is all from ZTF. And so there could be a calibration offset between the two, and even the ZTF paper talks about the photometric calibration of the ZTF survey being uncertain maybe at the 5% level. And so we included that as a systematic. Really, the idea of this paper is a proof of concept by being able to select your sample, you get this homogeneous sample with low scatter, and you can get this sort of parallel H naught measurement. The actual answer may depend on if the ZTF photometry changes a little bit, so that will change this number. But the idea, that won't change the scatter really, and it won't change the scatter here. It'll just change the offset between them. So the idea that this proof of concept, this method should work in principle. We could get more TRGB measurements of quiescent supernova hosts. Maybe even a bigger Hubble flow sample, and continue this work in terms of getting an H naught, a parallel H naught to Cepheid hosted supernovae, which are in star forming galaxies. Okay, one other thing we noticed after the fact was there was another calibrator galaxy that we had not included because we didn't realize that it met the criteria, but it does. That's supernova 1994D in NGC 4526. So if you include that one, then we get 6 calibrators, which is nice to go from 5 to 6. That one is a little bit low on the low side, so that changes our H naught from 75.3 down to 74.4. But other things don't really change. And again, you still see a very nice tight scatter for these objects. The scatter here kind of matches the scatter in the Hubble flow. That's really nice. We don't have some big difference between the two samples of supernovae. All right, so we were excited about this. We think it's a way forward in the future to do H naught in this sort of parallel way using early type galaxies. One question is whether you could extend this to high redshift. And here we have maybe a potential issue. We think we are selecting very old supernovae by doing this selection, right? We're picking massive quiescent hosts. The supernovae are likely to be old. Okay? And when we go to high redshift, well, those old supernovae in the nearby universe are not going to be there at high redshift. So the oldest supernova at any redshift is tied to the age of the universe at that redshift. Okay? And so if you have a sample which is deliberately picking out the oldest supernovae at all redshifts, you are naturally building in an age evolution to your sample that could be a problem. Okay, so for example, there's this paper, and I can talk about it more if you would like, just from this year, building on a series of papers, that says that there is a progenitor age effect, and that could be significant. If you pick a sample that is deliberately chosen to be old supernovae as you change in redshift, you might have an issue. For H naught, that's not a problem. Our objects are all old enough and low enough redshift where there's not much age difference. But as you go to high redshift, it might be an issue. So, for example, Rebecca Chen had this really nice paper for how do we do photometric supernova cosmology at high redshift. Using luminous red galaxies is a great way because you know that the supernovae are likely to be 1As. You can get the redshifts for luminous red galaxies. Photos these work really well, and you can do a photometric supernova sample with that way really, really well. The disadvantage, though, is and the hosts are homogeneous in that they're all early type galaxies, luminous red galaxies. Um, the disadvantage is if this really is the progenitor age effect is really important, then those luminous red galaxies at different redshifts will have different age supernovae, and that might show up in the analysis. So I think it's still a great idea to do. It may be more of a test of progenitor age than the best way to do cosmology with the least systematics, but it's certainly a great idea to look at these samples, and certainly that's what we're arguing to do at low redshift is to do these galaxies as well as the Cepheid star-forming galaxies. But when we push to high redshift, we have to be a little bit careful. Okay, I want to shift gears here. One of the points here is that we were able to find this homogeneous subsample with low scatter, and that's useful going forward. Can we find other ways to do that? And another way to do that is to work in the rest frame infrared. With the SALT 2 model, you saw that the peak magnitude that is used for the standard candle is the B band magnitude in the blue. But if you go back, I won't go back to the slide, but if you go further and further to the infrared, this light curve shape correction becomes less and less strong. And in the infrared, so for example, at J band or H band, there really is not much light curve correction that you need. And so you don't actually need to standardize the light curves. In fact, it turns out there's not much color correction you need either in the near infrared. And so actually in the near infrared, you can use Type Ia supernovae as standard candles. And so this was a paper that Sohail Dewan led a few years ago now, where we used this standard candle approach to measure H naught. We got something like this. This was updated in a couple papers using bigger samples. Again, you still find the same thing. One of the issues with the near infrared from the ground is the calibration. So the J band is sort of defined on both sides by the Earth's atmosphere. Excuse me. And so we wanted to check that calibration by going to space. And so there's this project, Syrah, that I led. The survey design, a lot of it was done by my postdoc at the time, Mi Dai, who's at Pittsburgh these days. Anyway, it was a program to use a Hubble Space Telescope to observe about 25 Type Ia supernovae in the near infrared from space to get that space calibration. So here, just to show you what this looks like, these are the objects with the HST images, beautiful. And then we had some which are even close enough to be calibrators, like this one, 21J. Fantastic, fantastic galaxy. And there it is in the HST image. So the HST data, actually, there's a paper by Justin Perel that's been submitted, so that should appear on the archive relatively soon. Then we're working on a couple other papers, the survey design paper, and we're working on an analysis paper. And I just wanted to show you some things from that analysis paper that's being led by Connor Larison. So these objects had not just HST infrared data, but they had ground-based infrared data and ground-based optical data. For HST, we're limited in how many epochs we could get, but from the ground, right, we can get really nice light curves. And so the idea is we take the ground-based light curves, that tells us the shape of the light curve and things like that, the time of maximum. But we use the HST data with the excellent calibration to pin the overall scale of the light curve. So the photometry is pegged to the HST scale, and we're going to use that HST infrared space calibration for the Hubble diagram. And so here's what it kind of looks like. Here's the Hubble diagram from these 20-some objects, one outlier from Syrah, from space in the space J band F125W with C3IR. And one thing you can compare here is a comparison to some ground-based objects from Luis Galvani. In the ground-based, you see the scatter is about 0.15 magnitudes. Again, this is the standard candle approach, no corrections. You can see from space, actually, we're doing a bit better than that. And so we think the calibration is an issue, and we're going to have this space-based calibration of near-infrared supernovae. So we'll apply this to H naught. We don't expect any huge surprises in the H naught application. We only have a sample of 20 objects, so it's not going to be, it's not going to change the bigger IR samples. But one thing we're very excited about this sample for is pushing for dark energy. So for example, with the Roman Space Telescope, we will be able to observe rest frame, maybe J or Y band to high redshift with Roman, and we can use this standard candle method to have better, lower scatter, a new way to get high redshift cosmology. Not maybe as far out to redshift 2 or something like that, where even the Roman bands give you rest frame optical. But if we talk about like redshift 1, where, for example, the cosmological results from DESI and other places show that there are slight differences, the dynamic dark energy versus lambda CDM, redshift 1 is a great place to work, and Roman will do a great job of rest frame infrared at redshift 1 with a big sample. So I'm excited to apply these kind of techniques to that. Okay, I'm running out of time, so I'm going to just conclude just some ideas of the future. I think the two big things on the horizon are Rubin. And with Rubin, what you saw here, right, like when we had this ZTF sample of 1,000 objects, we were able to cull it very specifically to get 100 objects that match the calibrators. With Rubin, we can play that game over and over and over, right? Match things with the same X1 and C and don't do any standardization. Match things with the same host types of host galaxies, star-forming galaxies, quiescent galaxies, etc. Okay, so that's what I think hundreds of thousands of objects with Rubin will enable is homogeneous subsamples and comparisons and systematic checks. So that's what I think I'm really excited for Rubin about. I've been working a little bit on Rubin on survey design. I'm part of the Survey Cadence Optimization Committee, and one thing that I've been working on is the survey, the observing strategy for the deep drilling fields. So if you haven't looked recently, take a look at the Ocean DDF observing strategy. It's going to get very high cadence observations of these fields, which would be great supernova light curves at sort of all redshifts that Rubin can reach. There's also Roman, so it's a part of the Roman, the ROTAC, and here one of the surveys that's going to obviously be great for Type 1a supernovae, designed for Type 1a supernovae, is the high latitude time domain survey. So you can again read more about that. Again, one thing I'm interested in is not necessarily the highest redshift, though that's very exciting as well, but rest frame infrared data for more moderate redshifts. I think that'll be a great science case for Roman that I particularly am excited for. Okay, so I will end with some concluding thoughts. It's sort of conclusions, but it's also going a little bit late. So I think we see clearly that there are differences in 1As, and there are variations of not just distances, but intrinsic properties with environment. And progenitor age could be a prime suspect. So with these bigger surveys, I think we have an opportunity to say we're not going to just take all our normal Type 1a supernovae and put them into one bin. We can split things up into making more and more homogeneous subsamples, test whether the cosmology is consistent among them, and then find the ones with the lowest scatter to use as the best standard candles. So I think you can get to do both things with bigger surveys and surveys like Roman, where we're expanding the wavelength coverage, for example, to a place where we will have better distances from the near infrared. Okay. And again, nearby supernovae, things, calibrators, things in the Hubble flow will continue to be extremely important. And this is a challenge actually for Rubin and Roman. For Rubin, it saturates for the bright supernovae. So we need to have clever ways of connecting Rubin and Roman and other things to more nearby supernovae. Of course, ZTF and things like that will continue. LaCie is coming online. I'm part of this shadowing program with DECCAM led by Dave Sand, again, to study nearby supernovae in conjunction with LSST. I think that's going to be very important as we go forward. Okay, and I basically tried to give this talk by saying, like, we don't really need to know what kind of the progenitor systems are exploding as 1As to use them cosmologically. I think that's true, but I do think that the more we know about them, the more we can shape which subsamples might be important or might be the most useful. And so we are learning a lot more about Type 1a progenitors and their astrophysics and their explosions. I didn't get a chance to talk about the JWST work, but feel free to ask me about that. I can show you some things, and I'm happy to talk about any other things, progenitor age, bias, etc., in the questions. So with that, thank you very much.
Thank you. Thank you so much. Very nice talk. And any questions?
Hey, Saurabh, that was a really good talk. Really enjoyed that. Since you raised that Sun et al. Paper, looking at that, there seemed like a couple of things going on. First of all, modern supernova samples actually correct for mass, and mass and age are correlated. So, when they derived their results, they backed out or didn't use the mass step that other people use. So, mostly I would say that isn't even present in the surveys. But also, they assume a really massive change in age, in progenitor age, which doesn't necessarily, probably is not actually going on, because it would require all low redshift supernovae to be super old, and yet we see them strongly associated, I think by a factor of 20, with star forming galaxies. What is this? Or I guess my question is, what's your take on the sun et al. Story, and similar, different?
Yeah, so I agree with what you're all what you're saying. I think the issue is that, right, that massive galaxies have older populations and that's correlated. So whether it's a progenitor age thing, so they argue that it's much more likely to be age than mass. And actually, physically, to me, that makes more sense, right? Like we don't think the supernova knows what mass galaxy it's in. But if you're making a correction based on mass, that will at least somewhat correct the age because exactly of the correlation that you mentioned, right? So it's hard to say that, oh, if you make a mass step, then you're just doing it wrong completely. I think you're probably getting some of the effect out, right? But the second point that you made is also, I think I totally agree with that. That was the big kind of striking thing to me, and that's why I actually made a little slide about this. So this is, I think, figure 1 or figure 2 of their paper. And if you look at if you look at this left here, so here's the typical age, and we'll just focus on the red and the dashed line here. This is the mean age of the stellar population that they think are producing type 1a supernovae as a function of redshift. And you can see at low redshift 0, their argument is that the mean age of a type 1a supernova at redshift 0 is something like 8 gigayears, which again, to me also seems quite old. So we know that, or we think that the delay time distribution for type 1a supernovae is something like a t to the minus 1. And that's what's indicated in this blue here. Now they have this kind of bump that comes up. And so there are DDT models that have DTD models that have an older population coming from, when red giants start to evolve and give you some older type 1a supernovae. So I'm not sure where this bump comes from in their model, but maybe something like that. But if you just assume the t to the minus 1, that says equal amounts of supernovae between 100 million years and a billion years, and 1 billion years and 10 billion years, right? So you would expect then, if you can have that whole range, you would expect that the mean of that distribution is going to be something like 1 gig a year, even at low redshift. Okay, so that's quite a bit different than 8 gigayears that they have here. Now, one thing that's different, though, is that the star formation rate changes with cosmic time. So they include that effect. And their argument is that the star formation rate today is low in the universe compared to when at cosmic noon at redshift 2. And so because there was a much higher star formation rate, there still are more older objects that will explode. And so you have to take the DTD, convolve it with the cosmic star formation history, and that's what leads to this number here. So I think there are details there about exactly how you do that, exactly what delay time distribution you use, that I think you could probably change this number significantly. So I think more work needs to be done there. But I think there's actually a really pretty easy test for all of this, is because they're treating the whole sample at any redshift together. But we know what the hosts are at these different redshifts. And so, for example, we can do a high redshift cosmology with only star forming hosts. Just like you did with the calibrators, right? When you were like, okay, all the Cepheid calibrators are star forming. Let's make sure to only have star forming hosts in the Hubble flow. Or like Max's paper, like I talked about, we're using TRGB calibrators for quiescent galaxies. Let's make sure we have quiescent galaxies in the Hubble flow. We can extend that pretty easily to high redshift. And if this progenitor age effect was as big as they say, we would see a clear cosmological difference between a sample of star-forming galaxies and quiescent galaxies, or the average galaxy at high redshift. So
or even at low redshift, right? Because at low redshift, where you have both types, you would have, the quiescent ones would definitely be the old ones, and the star forming galaxies would be the young ones. And I mean, this goes back to 1998. It was one of the first tests we did, was to compare those two samples, and saw that we got consistent distances.
So there, that 10th of a magnitude mass step might be the same thing there, as you said, right? So,
Okay, thank you. Leandros?
Yes, hi, thanks for the nice talk. Can you please show again this nice histogram you had with the supernova versus H node, where you had the number of supernova versus H node?
You mean maybe like this one?
No, before that. No, before that. Well,
This one, perhaps?
yes, this one.
Okay.
Okay, here we see that there's a very big spread of H nodes starting from about 60 to 85. Have there been any investigation to see, is it a purely statistical spread, or there are some common features in high H node and low H node supernova? Have you looked at possibly systematic differences between the two ends of this distribution?
Yeah, I have not. So I mean, one thing is that you can figure out what the width of this distribution should be from the Hubble flow supernovae, right? So you are combining this sample with a Hubble flow sample, and the Hubble flow sample, let's say, has a scatter of let's make it easy, 0.2 magnitudes, and that would be a 10%, scatter in supernovae. So that would say that when you make your calibrator sample, whatever the mean is, you would expect a width here of 10%, 1 sigma. And that's what you see, right? So 1 sigma here is about 10%. And so there's no evidence that this scatter is anomalously large. But then your question is, okay, now let's look at the ones over here and the ones over there. Are there some systematic properties? And that would be true both of the calibrator objects and the Hubble flow. And so, yeah, people are looking to see, what makes the supernova a little bit brighter, and that's how the mass step was discovered, right? Like, oh, there were the more massive host galaxies were, coming on one side. And so, yeah, people are doing that kind of thing. My hope is to try and find subsamples where the scatter is smaller so that those tests become more sensitive, right? The things that are on the edges, are suddenly they're not just 2 sigma events, they're 3 or 4 sigma events for a smaller scatter. And then you really could say, aha, this is different because of X, Y, and Z reason. But yeah, it's a great idea what you're talking about.
Okay, thank you.
Any other questions? I had a question. So can you go ahead, I think, a couple of slides when you are using different calibrators, supernovae calibrators, and the value of the Hubble constant goes from 75.3 to 74.4.
Oh, yeah, that's just one object difference. So yeah.
Yeah, exactly. So can you say a bit more why just one object is changing H naught of 1 kilometer per second with megaparsec, and why the error is not changing at all instead?
Yeah, so the error here is dominated by the 5% error from the systematic uncertainty in the ZTF offset potential so you can see the difference here. Okay, 1, 2, 3, 4, 5, they're the same, and then we add this one more. And it just pulls the mean down a little bit, but the overall scatter is, it's totally consistent with the overall scatter. So this, with the quiescent sample, we only have 5 or 6 calibrators. That really is small number statistics where adding one will change things like this, but it doesn't seem to change the errors very much. We redid the full standardization, including this. So actually, if you look at the Hubble flow, that also changes very slightly because the standardization parameters change, because even adding 1 to a sample of 100 and some, it changes things. So I think this is totally expected statistically. Yeah.
Thank you. Any other questions? No? Okay, so thanks so much. Thank you so much.